Today we're going to be talking about section 1.4, other function qualities. We just finished our problem of the day working on finding the rate of change and the initial value. We got to continue to get better at that as well. So let's start by doing a little reading and highlight. You should already have some stuff highlighted. I just kind of want to go through it a little bit, step by step, and see if you're grabbing what you should be grabbing. So far, we've been describing graphs using quantitative information. Who can tell me what quantitative information is? Yes, dear. Information using numbers. See how it's right there, using numbers. Specifically, we've described linear functions or linear function graphs using rate of change and the initial value. What is rate of change? Calm down. Don't everybody speak at once. We got time. What is rate of change? Yes, sir. Slope. That's another name for it. Yep. Y-intercept? No. Rate of change is not the y-intercept.
Isn't the y-intercept slope?
The y-intercept is not slope. What is rate of change? Rise over run. Yes. Rate of change is rise over run. Rate of change is slope. Rate of change, like that sounds like pretty straightforward to me. How quickly something changes. Rate of change. How quickly or slowly something changes. Yes? We also talked about delta x over delta y. What does delta mean? Delta y, I think I just said that backwards, over delta x. What does the Greek symbol delta mean? I'm sorry? Change. Delta means change. The change in the y. And the y is vertical, so rise over run. Right? All right, come on now. The rate of change is how quickly it changes, how steep it is, what its slope is, blah, blah, blah. All right? And what's the initial value? The y-intercept. The initial value is the y-intercept. What else is it? Good morning. What else is the initial value? Like you've got 4 things written in your notes somewhere about what initial value is.
When the input is 0.
When the input is 0. There we go. Now we're getting somewhere. Anything else? There's one more, and it's hard to find. It's the constant. Initial value is the constant at the end of an equation. What's a constant? Just a number. You have a number by itself at the end. That's your y-intercept or your initial value. Okay? Both numerical data, however, at times is more beneficial to describe in a qualitative manner. This means the qualities or non-numerical characteristics of the function. Okay, that's what we're going to be talking about here today. Okay, first, what is the definition of a linear function? Here are some examples of linear functions in an equation, table, graph, and story form. So, notice that I highlighted in yellow the initial values. I guess I missed one. Get that one I missed. Right? What is our initial value? It's our value when the input is 0. See that in the tables? You see that in the tables? Okay. Our initial value is also our y-intercept. Can you see that now in the graphs? And then our initial value, a carnival charges $3 to enter. That's the initial value. The company makes one sweater for every 2 pounds of wool it has, but it doesn't say anything else, right? So there's no initial value in there. And what number do we represent what number do we use to represent the lack of anything? 0. Okay. And then a plant has a height of 5 meters. That's the initial value. Are you with me?
Yeah.
Okay. And then how about rate of change? Notice in the table, each one of these in this first table goes up by 2 every time. What about the second table? How much does it go up every time? 0.5 or a half. How about the third one? How much does it go up each time?
1.
Here's something interesting. Look at that 2. Look at the 1/2 or 0.5. Look at the 1. Do you think that's a coincidence? It's not. Okay, when we're dealing with linear functions, remember the most important or the most common way we see it is y equals mx plus b, right? Where m is the rate of change and b is the y-intercept or initial value, right? When linear functions are given to us in that way, they should be easy to see your rate of change and your initial value. Y'all with me?
Yeah.
Do you see rate of change and initial value in the equations, the tables, the graphs, and the functions or the situations at the bottom? Can you see those? I hope so. What do you think makes these functions linear? That they're a straight line. They are a straight line. Okay. Here are some examples of nonlinear functions. Nonlinear functions. Notice some things that are different. What kind of things do you notice that are different? Yes, sir. They all have a curve. Excellent. Or not straight. Do you notice anything about the tables?
Yeah.
What?
How the top number is always 1, 2, 3, 4, and then the bottom numbers are 7. So the second one goes up by 2, and then
Now look at how they go up. Notice those things I have written in red? Like the first one. The table goes down 5, down 7, down 9, down 11. What happened in the linear functions?
they all went up to 1.
They went up by a constant rate of change. Okay, so linear functions have a constant rate of change. Nonlinears do not have a constant rate of change. Okay? Look at the equations. I hope that you notice something in the equations. What I hope you notice, say again? The exponent. Look, there's an exponent there. There's an exponent. There's an exponent. Was those exponents there with the linear functions? Absolutely not. Absolutely not. Okay. A linear function makes a straight line when it's graphed. A nonlinear functions are not linear. So if it's a straight line, it's linear. If it's not a straight line, it's nonlinear. That should be pretty simple and straightforward, yeah? Graphing may be the quickest way to tell if a function is linear or nonlinear, but we can also determine a function is linear by its input-output table. Here's 3 input-output tables right below. This can be seen in the input-output table that there is a constant difference. These 3 tables right here are examples of linear functions. Notice that the rate of change or the difference is constant. It's the same every time. Yes? We call that a constant difference. Notice that the first table has a constant difference of 2, meaning that t increases by, as t increases by 1, the function or c of t increases by 2 every time. The second difference of a half and the third has a constant difference of 1. Isn't it amazing how this is all read? This is all just your reading, isn't it? Are you learning? Are you grabbing anything? Alternatively, notice that all three equations have the independent variable only to the first power. There is no exponent there. It's to the first power. Can you see that?
Yes.
I hope so. This also means that they're linear functions. Check the nonlinear functions given on the previous page. We already looked at those. They all had what? An exponent or a power, yes? They had no constant difference, and they were not a straight line. In general, there's that form, fy equals mx plus b, right? Y equals mx plus b. It's considered a linear function where m is the slope and b is called the y-intercept. Notice that x has an unwritten exponent of 1 with it. So, if I give you an equation, how are you going to determine whether that equation is linear or not? No. By seeing if it has an exponent. I'm about to give you an equation. Are you ready? Back to y equals 3x squared minus 4. Linear or nonlinear? Why? How about this one? Y equals x plus 5. Why is it linear? Because the exponent is 1. Okay. Now, there are other forms that you can get of linear functions, like standard form, ax plus by equals c. We're not going to spend any time on that right now. Okay. Now, you're going to need to write all of this down. Okay. This isn't in your reading anywhere. Now, you just told me that given an equation, something is called linear if its degree is 1, right? If it has no exponent or it's to the first degree, that's called linear. Yes?
Yeah.
Okay. How do we name functions? By their degree, by their highest power or exponent. That is known as their degree. For example, y equals x. What degree is that to? It is to the first degree. Does that make sense? Y equals x squared. What power or exponent is that one to? Thanks, sir. It's to the second degree, or power or exponent. The next one down, y equals x to the cubed, or to the third. What degree, power, or exponent is that one to? It's to the third degree. What about the next one? Yeah, everybody jump in. Next one. Everybody said. You guys see what I'm talking about here? Are you with me? What power is it to? The fifth. And the last one? To the sixth. Now, that power or degree determines the name. Okay? Can I tell a story?
Yeah.
So there's this little boy. This little boy tugs on his mama's dress. He says, Mama, Mama, why is Standing Bear named Standing Bear? He says, well, when Standing Bear was born, when we walked out of the tent, the first thing we saw was a standing bear. Oh, okay. Mama, 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 why is Soaring Eagle named Soaring Eagle? Well, when Soaring Eagle was born, the first thing we saw when we walked out of the tent was an eagle soaring overhead. Oh. Mama, Mama, why is Running Deer named Running Deer? Well, because the first thing we saw when we come out of the tent was a running deer. Why do you ask, dog squatting? Thanks. Somebody got it. Thank you. No?
Dog spotting.
Okay. How were they named?
After the things they saw.
After the things they saw. But here we're talking about functions. How are functions named? And everybody said by their degree. How are functions named? How are functions named? By their degree. Something to the first power is called linear. Something to the second power is called quadratic. Now, I understand that doesn't make any sense because you think of quadratic and you think of what? 4. Okay? Why in the world would they give something to the second power a name that sounds like a 4? Right? Here's why. Would you read that? What is that? X to the second power. Somebody else read it. Somebody read it differently. X what? X what? X what? Squared. X squared. Everybody knows that's the nickname for something to the second power is squared, right?
Yeah.
It's the nickname, yes? You know, like when you call a really big guy tiny. Or when my friends call me slim. Don't be laughing at that one. Stop laughing.
What?
Something to the second degree is called squared. How many sides does a square have? 4. Thus, quadratic. It's called quadratics because of that. Are you with me?
Yes.
I don't know if that'll help you remember it or not, but something to the third power is cubic. Something to the fourth power is quartic. Quarters. There's 4 quarters or in a dollar. 4 quarts in a gallon. Quartic. Something to the fifth power is quintic. I know for you Avenger fans, the Quinjet has 5 engines. Anything beyond that does not have a special name. It's just by the power. So next one will be to the 6th degree, 7th degree, 8th degree, 9th degree, and so on. That's what I want you to get today. I want you to get these names and how are they named. How are functions named? Thank you. By their degree. How are functions named?
By their degree.
And then you have to learn these names. Okay? By their degree. Next, last thing I'm going to give you is their graphs. A linear function is a straight line. A quadratic, you can. A quadratic is a U-shaped graph called a parabola. A cubic doesn't have necessarily a name, okay? But it goes something like that. It's got a little swerve in it. A quartic looks something like a parabola. It's just got a little junk in the middle. A quintic looks kind of like a cubic, doesn't it? Just got a little junk in there. Anybody want to guess what they think a 6th degree is going to look like? Now, I want you to notice odds and evens. 1, 3, and 5 are like John Travolta's, going in opposite directions. Staying alive, staying alive. Right? They're going in opposite directions. Opposite odds are going in opposite directions. The evens the ends are going in the same directions. Okay? Quadratic, quartic, 6 degree. Notice that those graphs have both of the ends going in the same direction. Okay? All right, I'm going to move on from there. You ready? 3, 2, 1. Last part of this information that was given to you in section 1.4 is the qualitative data increasing or decreasing. Now, this should be pretty straightforward. And what I want you to remember this is it's always from left to right, just like we read. We're always moving from left to right, just like we read. And it's an increasing function if we're going up from left to right. It would be a decreasing function if we're going from left to right. So these three, quickly, you can see they're all increasing. Now, the other thing, when we're talking about linear functions, increasing would have a positive slope. Decreasing would have a negative slope. That's pretty simple, yes? Increasing, decreasing. Well, linears are really, really easy. However, there's also one where you're flat. You know, if you're walking across it and it's flat, it's called constant or no slope or zero slope. Okay, or zero rate of change. However, nonlinear functions can be both increasing and decreasing. For example, look at this one, this parabola. It's increasing until it gets to the very top, and then it starts decreasing. We were going from left to right. Okay? Now, when that happens, when they're increasing and decreasing, okay, for example, let's look at this particular graph right here. From here to there, it's increasing, right? But it's also increasing from here to there. Does that make sense? Remember how we look at the domain? So this one is said to be increasing from negative infinity to negative 2. It's increasing. But it's also increasing from 2 to infinity. Are you with me? Okay, what's it doing in the middle there? It's decreasing. Where is it decreasing? From negative 2 to 2. I know I didn't spend a ton of time on that, but I hope that you can see that. We can look at the domain and tell you when it's increasing and when it's decreasing. Okay? These data also are said to have a maximum or a minimum. You've seen maximums and minimums before. Maximum is the highest possible point. Minimum is the lowest. And then sometimes they have what we call a local or relative maximum or minimum. We all see this function right here? Does it have a maximum or a minimum? Well, it doesn't have either. But if I zoomed in like this and that's all you could see, you would say, hey, that has a minimum, wouldn't you? And then if I moved over here and that's all you could see, you would say, hey, that has a maximum, wouldn't you? Those are called relative or local maximum and minimums. Are you with me? You've seen those before? Yes? All right, your homework is 1 through 42. Look, 1 through 42 even, and I don't want you to watch a video tonight. I don't want you to watch a video, and I don't want you to check it. I just want you to do 1 through 42 even, following directions. Got it? You got 4 minutes. You can probably get like 6 or 8 questions done. Yeah, you can use your book. Absolutely. Got that one. Got that one. Got that one. Got that one. Done. Oh, this is a little harder. Got it. Got it. I already did the whole first page. All you have to tell us whether it's linear or nonlinear. Do me a favor. On numbers 13 through 18, which is the second page, instead of just doing the evens, do one, because they each say, give me two of this, give me two of this, give me two of this, right? Instead of that, give me one of each of those on the second page, 13 through 18. Give me one of them. Like number 13 says, give me two examples of a linear function in equation form. Just give me one. And then do number 14. Give me one example. Number 15, give me one example of a linear function in graph form. Number 16, give me one example of a nonlinear function in equation form.
You want us to do all of them, but just one?
Yes. So 13 through 18, you're doing all of those, but just give me one for each. Are you with me?